very much, and I would like to thank all the organizers, especially Professor Graf, for the invitation, and it's a wonderful city to be in, so thank you. So I will talk about the configuration space of most endpoints on the circle. A lot of what I say is not really about the circle, it could be anything, but all the examples will be on the circle. So I have been interested lately in what we call n-valued maps. This is a multi-valued function where the number of values equals n, exactly n, not less than n and not more than n. This is called an n-valued map. And everything that I say, the space will be a compact polyhedron, and the map is continuous, upper semi-continuous. Actually, if you require it has exactly n values, then any upper semi-continuous is automatically lower semi-continuous, and it has all the continuity that you might want. The maps I'm talking about on the circle, at least, they look like this, very sort of well-behaved. This one right here is 3 values because each domain point has 3 values, all right? S1, the circle I will always consider as the interval with the endpoints identified. So for this to be continuous, this point here must be the same y value as this point over here. All right, and remember, n value, when I say n value, I mean exactly n, no less than n, all right? And there is a nice Nielsen fixed point theory for n-value maps, which was defined in the 80s by Helga Schirmer. And then not many people were interested for a long time, and then Robert Brown in the early 2000s started to do this kind of thing again, and now it's become more popular. And the Nielsen fixed point theory, it works nicely because, I don't know if you can see this diagonal line here, but the intersections with the diagonal, if you look only locally near this intersection point, it looks like a single valued fixed point. You can just ignore all of the other ones. So locally you can still define things like the fixed point index, the fixed point classes, all of the other usual things, they still work in this setting. All right? But it only works when there are exactly n values. If somehow this, if you can imagine, if there were less than n values at certain points, maybe because these red lines, they cross and they make one point, which is kind of like a double, then it's not obvious what the fixed point index should be at such a point. So there's problems if you have less than n, but if it's exactly n values all the time, no problem. All right, and there is a nice configuration space viewpoint for n-value maps. Probably you are familiar. This would be the set of unordered configurations on endpoints, which I'm going to call Dn. This is just the set of all n-element subsets of your space, exactly n elements, n distinct elements. All right, and any n-value map is equivalent to a single-valued map where you just associate each point of x becomes a set of n elements. This is obvious point of view. And it is interesting to talk about the topological properties of this configuration space, Dn of x. For example, a single element of, say, D5 of R2 might look like this. There are 5 points in R2, so this is one element of the 5-point configuration set space. Or maybe it could look like this. And you can ask topological questions about, is there, so for example, an easy question, can the configuration here of these 5 points, can they be moved around to become this configuration without colliding? And the answer, of course, is yes, it is. And what that means topologically is there is a path in this 5-point configuration space, a path from this configuration to this configuration. And in fact, it's fairly easy to see if you know what I'm talking about. The configuration space of R2 is path connected because any configuration of several points can be rearranged inside of R2 without colliding to any other configuration of several points in R2. But it's not true for other spaces. For example, these two similar looking spaces, just a circle, and this is an annulus, they have different topology in their configuration spaces. So in this case, if you were looking at configurations of 4 points, the fundamental groups of the configuration spaces are different. Because, for example, on this one, you can have a loop of these points, all these points move and then come back to where they started. It is possible in this one to have one guy go around and come back, and the others stay still. But it's not possible here, because they're not allowed to collide. On the circle, you cannot have one guy go around and the other 3 stay still. But if you have extra room on ends, you can. So I'm saying the topological properties of the configuration space are interesting to talk about. All right. These come up in applications, which I know essentially nothing about, but they are the appropriate setting for the mathematics of coordinated motion planning. If you have a lot of individual robots or things that need to move around without colliding. For example, if you have one of these like drone light shows, this is this particular motion, if you have all of these little things moving around, would be modeled in this configuration space D250. I counted the dots here. There's 250 of R3 because they're moving inside of R3. All right. So Dn of x is the configuration space for non-colliding points. What I would like to talk about is a configuration space for at most n points, which is the same thing really, but we will allow collisions. And I'd like to talk about some topological properties of this kind of configuration space. All right, this would be the proper model for a function which has less than or equal to n values. At most n values is what I'm going to call a function like that. All right, so such a function looks like this, and I'm going to call this function at most 3 values because each x value here has, mostly they have 3, but sometimes when these lines cross, there's only 2. So this we call at most 3-valued function. And I want to describe the appropriate configuration space for these kinds of maps. All right? And there have been several, I will say, mostly equivalent approaches. I say mostly because this is still somewhat work in progress, and I'm not entirely sure if they are totally equivalent, but this is part of the project. Did I mention, I didn't say at the very beginning, this is a joint work with Daciberg Goncalves in Brazil. Sorry, I did say his name, but I didn't say it out loud. Sorry about that. Anyway, this one in particular is fairly easy to handle in terms of a configuration space because this map consists just of 3 separate single value maps. You can see there's one across here, there's one up here, and then this one here is in 2 little pieces, but that's one map on the circle, all right? This consists of 3 separate single value maps, and so we can think of this as one map into the codomain, but to the 3rd power, the 3rd, Cartesian product. All right, so this n-valued map, at most n-valued map, can be modeled as a map into the space y to the power n. In this case, s1 to the power 3. But this is not always possible to do, to write these as maps into the Cartesian products. For example, here's another one. This is at most 3 values, but you will notice in this case, come on in, you actually cannot break this into 3 individual functions into S1. F, in this case, does not decompose into 3 different maps. The problem is this, you still have basically 3 lines, but you have this line and this line here. Individually, they do not make a map on the circle because the starting point and the end point don't line up like they should on the circle, all right? If you really try to work out the numbers here, you could say something like, okay, f of 0, apparently these 3 values are 0, 1/4, and 1/2. And then f of 1, if you follow the same lines across, those values would be these ones. 1/2, the first point. The 1/4 point ends up here at 1/4, and then the 1/2 point ends up at 1, right? But now you see these are not equal, right? But in order to be a legal map on the circle, continuous map on the circle, it has to have f of 0 has to equal f of 1, but they're not. So this is not a continuous map. Into S1 to the power 3. All right. The problem is these 2 points are not the same point. The issue actually is the ordering because the points their coordinates are the same. I have 0 and 1, but on the circle 0 and 1 are the same point. The only issue is the ordering. So the natural thing to do in this case is I want to use something like the product here, but I would consider only things equivalent up to their ordering. All right. And this, maybe you've heard of, this is called the symmetric product. So instead of y to the n, we use y to the n mod the symmetric group. So this is all n tuples from y, but we consider them as unordered. All right. This is the symmetric product, and this is a well-known thing that people talk about. And in fact, there is a Nielsen fixed point theory. You know, my point of view behind all of this is Nielsen theory, so I will mention this every so often. There is a Nielsen theory for maps into a symmetrical product by Massey in the 70s. And also there was another idea by Shermer. She wrote a paper about what she calls a bi-map, which is a function who has every point in the domain has either 2 or 1 value. So it's a multi-valued function, but the number of values is always either 2 or 1. And these two theories agree with one another. Actually, the bimap theory is the same as SP2. Yeah, the bimap is just the case n equals 2 of this thing. All right, these maps into symmetric product actually have a little bit of extra regularity to them. For example, here's a nice example of a map into the symmetric product. If we look at this point in particular, we can see one of the values is this 1/4, and the other value is 3/4. But there is some sense in which you can tell just by looking at the picture, this is like a double value of 3/4 because it occurs at a crossing of these two lines. If you were to, say, move the x value very slightly to the left, you would see this point actually represents kind of two separate points which happen to be coinciding at that one moment. So this, as a map into the symmetric product, you would write it this way. 1/4 and then 3/4 appears twice. All right. In this way, it is possible to look at one of these symmetric product maps and assign to the various values sort of a weight. I can say all the points in red, they are like a weight 1. They represent really a single value. Whereas these points in blue, I'm going to say those are weight 2 because they represent kind of 2 copies of the same value. All right. All of these points have weight 1, except 3 of them have weight 2. And the weights have a nice sort of local summation property, in the sense that like this is a weight 2 point. If you move it slightly, it will break into 2 weight 1 points, and the weights of the 2 always sum up in the way that you would expect. All right. Here's a slightly fancier example. This is one in which this line actually goes along with the other line for not just a single point, but for an interval of time. But no problem. All right. This is a map into SP2, and we can also consider it as one of these sort of maps with weights assigned. All right. And it turns out this, I'm not making this up. There's a well-known theory of what is called multi-valued weighted maps, which began, I understand, by Darbo in the 1950s, and then a fixed point theory was developed for these things by Daciberg in the 70s, who was here somewhere in the building probably, and by Robert Skiba more recently. So these things have also been studied. And in the setting that I'm talking about, I believe that a map into the symmetric product is equivalent to one of these multi-value weighted maps where the weights are required to be positive natural numbers. So the general theory of weighted maps allows the weights to be any weights from any ring or something like that, but if you consider only weights which are natural numbers, then you will get the same thing as what I've been talking about, these symmetric product maps. All right, and of course, so symmetric product maps into SPN are ones for which the sum of all the weights add up to n for every point. All right, so the class of n-fold symmetric product maps is basically the same as the positive natural number weighted maps, where the weights sum to n. That's what I'm trying to say here. And actually, there is yet another viewpoint which is equivalent to these two other ones. The same type of maps have been described in a different way by Michael Crabb in the 2010s. Here's Crabb's formulation. We consider an n-fold covering space x hat to x. So this x hat represents something like x, but it's been copied n different times. It could be actually disjoint copies of x, but it could be some more complicated covering space. We replicate each point of x n times. And then we consider a single map from x hat into y. So what we've done sort of is duplicate every domain value into n separate domain values, and then we map all of them over into y. All right. If you think about it, if you consider this thing, you do the inverse of this covering first. So you start in x, pull back to n different values, and then you push them over with f. What results is a multi-valued map with cardinality at most n. All right, and this I will write it as a conjecture because we haven't, like I said, this is still somewhat work in progress. But the following classes of maps are all the same. So these symmetric product maps are equivalent to the weighted maps with weights in the positive natural numbers, and these also are equivalent to this kind of n-fold covering maps defined by Crabb. All right. One more equivalent characterization of these kinds of maps. One of these, maybe you already thought about this. One of these maps into the symmetric product, or a weighted map. You have single values here, but some of the values are occurring twice. This I hope you will immediately realize, is a union of these two things. And these two things individually have exactly n values. So this one has at most 3 values at each point, but it can be decomposed into a 2 value plus a 1 value. All right? So our map into SP3 is actually a union of a 2 value and a 1 value. I mean exactly 2 and exactly 1. All right? And this seems to be always the case. This one I'm actually less sure in terms of conjectures. I'm less sure about this one than the other ones. But maybe you have to change these maps by homotopy for this to be true. I'm not totally sure. But anyway, I'm going to add this into the conjecture. This same class of maps also includes all finite unions of individually ni valued maps. So these individual ones have exactly the same amount of values, and we union them all together in a case when the n's sum up to this n. All right? This is kind of the first part of the paper that I've been working on with Daciberg. And in all cases, the proper configuration space for these maps is this symmetric product space, as described in the first category there. All right? But in my remaining 10 minutes, this class of maps into SPN actually does not include all of the at most n value maps that I'd like to talk about. There are some more kind of exotic examples which do not fall into this class. So here is, it's not terribly exotic, here's an example. It's not obvious when you look at it immediately, but actually this is at most 3 values. Every domain has either 2 or 3 values in this example. But this cannot be expressed as a map into the symmetric product, the threefold symmetric product, or weights or whatever. This cannot be realized, I'll explain why. It can't be realized as a weighted map with positive integer weights. It's because you could try to assign some weights. Now, because of the local properties of the weights, if I make one of these weights C, then actually this entire arc is all of these points will have weight C because of that local summation property. And I'll just label these A and these B. I'm just trying to make up some weights. Now, because this is a circle, it means if this is C, actually this also has to be C, because that's the same. So they also have to do this. But now you have a problem with the local summation property, all right? The weights have to sum up, so this point right here, its weight must be C, but also C plus B. And this cannot be achieved with positive integer weights. The B would have to be weight 0, which I'm not allowing, all right? So this one right here does not fall into the category that I was talking about before, but it is still one of these, it has at most 3 values, so I still want to be able to talk about this kind of thing, all right? So SPN, the symmetric product, is not actually the appropriate configuration space for what we are trying to talk about in this case, all right? So what is it? Well, it's something else, I guess. As far as I know, this is a new thing. We just call it Cn of x. It consists of all n element subsets of the space where there is no condition about distinct elements, so these elements may be matching some of them, and we use the Hausdorff metric to make this into a topological space. So I'd like to just briefly try to describe the topological properties of this configuration space. It's different from Dn of x. And here's one big difference. This is actually, the proof of this is totally straightforward. If x and y are homotopy equivalent, then these configuration spaces are also homotopy equivalent. This, I don't know if that seems obvious, but this is not true of the D configuration spaces. Remember, those two configuration spaces have different fundamental groups. But in terms of this C configuration space, allowing collisions, they are actually the same. All right. Oh yeah, so in terms of trying to look for interesting examples, this means if x is contractible, then this configuration space will also be contractible. And so that means the configuration space of the interval or of Rn, these are not, they're not interesting to talk about. The first kind of non-trivial example would be the configurations on the circle, which is the title of the talk. We can build this as a simplicial complex fairly easily. It would be all sets which, let's just look at C2 first. It would be all sets of either 2 different points or just 1 point in the circle. And we can draw that as a simplicial complex like this. This is all 2 points. Let's just assume the first one is less than the second one. You get this triangle. The left edge is all ones where one of the coordinates is 0, and the top edge is where one of the coordinates is 1, but those on the circle are equivalent. So we have to identify the left edge with the top edge. And we get this kind of identification space. And if you think about the arrows and such, this is a Mobius band. So Apparently, this configuration space on S1 is a Mobius plan. If you want to do this with 3 points, you can do the similar kind of cell construction. We get one vertex, 2 edges, two simplices, and 1 3 simplex. If you work through the combinatorics of this stuff, it's fairly straightforward. These faces actually have a nice property to them. Every face in here might include the 0 vector, some of them do, and they might include, I write this 1 vector, that's this one here, it has 1 in every coordinate. Some of them include both of them, some include neither of them. I'm going to call, say one of these faces is extremal if it includes both of those, the 0 and the 1, or non-extremal if it doesn't include both of them. And then it's not so hard to work through the combinatorics here. It turns out when you do this identification of various faces and whatever, all of the extremal faces get identified and all of the non-extremal faces get identified. And these are the complete description of all of the identifications you get in this complex. And so what that means is this as a simplicial complex, you get 2 simplices in each dimension. There's the extremal one and the non-extremal one. Apart from the top and the bottom dimension, there's only one because there are edge cases, all right? 1 simplex in each dimension for the top and the bottom, all right? And it's not so hard if you, again, do the combinatorics. You can actually compute the boundary maps, and so it's not so difficult to, you can know everything. If you work out these boundary maps, you can see in odd dimensions the boundary map is 0, which is going to make all the homology groups are 0, except possibly at the top and the bottom. And it turns out, actually, that's exactly what you get. You get, when n is even, you get this thing, which has the homology type of the n-dimensional sphere. And when n is odd, you get this, which is also a sphere, but of 1 less dimension. We have no real sort of theory about why this should be the case, but you can compute it by the cell complex. So this configuration space on S1 is a homology sphere of dimension n or n minus 1, depending on the parity. All right. We can also talk about the fundamental groups of these things. You know, I already said that for most of them, the H1 is going to be 0. So we expect the fundamental group to be trivial also, at least when n is greater than or equal to 3. This actually you can visualize with some cute pictures, which I hope you won't mind if I share in the last few moments. It turns out, just talking about fundamental groups, loops can unwind in weird ways if you permit 3 or fewer values. And here's some nice pictures that I made up. I'm going to visualize a loop around the circle S1. I think of it kind of like this is like a surface braid diagram or something. So this, if you think of time going vertically, this is a loop going around the circle 1 time. All right. And I would like, and a homotopy on this diagram, you will see a homotopy by bending the line around in some way. And because of the setting that I'm talking about, we are also going to be allowed to split the line into either 2 or 3 other values when convenient. At most 3 in this case. All right, so check it out. I'm going to do a homotopy of this thing, which will look like an ordinary homotopy, but also you're allowed to split each point into at most 3 points. So first I'm going to just kind of double out all of these values into 2 points each. And now if you bend these guys here, you can make them come close together. And in fact, you can make them meet in the middle, all right? So this is a valid homotopy in this configuration space. This is already somewhat strange in my opinion. I have what is sort of like a degree 1 wrapping, has been transformed into a degree 2 together with a degree 0. This is weird in my opinion. But so far, I've only used 2 values. So this kind of motion can be done even in the 2-value configuration space. But if you allow me 3 values, I can do this. Here's a very strange step. I'm going to, well, you'll see, take this part here and just pull it back a little. And now you'll see like a slice like this. It uses 3 values. There's 2 on the front and 1 on the back that you can't see. All right? But now, this sort of rectangle here, you can just pull it all the way around the back side and around the front, and it becomes trivial, all right? So, if you allow me 3 values, this just single loop around the circle is actually contractible. Very strange, but this, you know, I was trying to explain why you should believe me when I say the fundamental group of this thing, if n is 3 or more, we expect the fundamental groups to be trivial. All right? Yes, this is what I said. Maybe this is true in much more generality. You know, I'm just doing the circle here, but I feel like if a loop around a circle is contractible, then it should be contractible inside of anything. What else could it look like? I don't know. All right. But I will just mention again, I believe this contraction that I did here is not possible using like 2 values. You can make it into that strange sort of 2 times with a 0 times, but I don't think you can contract it entirely. All right. So it seems like the space of maps with at most 20 values is quite different if you're talking about 2 values versus more than 2 values. And we already know that when in the case n equals 2, there is a nice Nielsen theory, the bimaps theory, or also this theory of SP2. This is probably because our theory about less than or equal to 2 points is actually the same as the symmetric product theory, only for n equals 2. If you make higher n's, then they become different theories. All right. As I mentioned, there's already a Nielsen theory for bimaps and so on. And it seems to me that there cannot be a nice Nielsen theory for these kinds of maps when the n is more than 2. Something like this is going to be a real problem. This is, again, my strange example. Here, we have 2 fixed points with local index of 1 each, I guess. But if you move this kind of cross piece over here, I've introduced a new fixed point without, if I think of the fixed point index being preserved by homotopy, this doesn't look good to me, because I just created a new fixed point which doesn't seem to have index 0, but it adds in with the other 2 fixed points have not been changed locally. So I don't expect fixed point theory to work very nicely. All right, that's all. Thank you very much.